In this video, we are going to write a program that reads the voltage coming from the potentiometer. We'll start with the skeleton code, which consists of only the include for the io.h, the AVR standard include file, the main, and the never-ending loop. Let's start by putting in some pseudocode on what we would like to do. First, I know I want to include the use of the LCD to put in the actual number that the ADC gives us, the analog to digital converter will give us, and we'll display that right on the screen. We really already know what we need to do to get the LCD working, and that's just include the Mr. LCD.h file, and we're going to include add the initialize Mr. LCD. This is a capital I. Next, we want to configure the analog to digital converter. And this will generally happen not in the endless loop. We have two options when it comes to the function of the analog to digital converter. And the two options is having the ADC start the conversion through interrupts, or finalize conversions through interrupts, or through just determining if a flag is set or not, and then reading the results. For this tutorial, I'm going to be selecting the option of using the interrupts. We won't actually have to use our never-ending loop, but we want to maintain it so the microcontroller essentially stays on the whole time. So outside of this, we're going to add the interrupt routine and display the results. Since we know we're going to be using the interrupt, we have to turn on the global interrupts, so we're enabling, and we know this from the interrupts tutorial, we always have to enable the global interrupts if we're going to be using interrupts at all. The ADC also has to be configured to use the interrupts, and since we're using interrupts, the ADC has to enable its own interrupt function. We need to also decide whether we want 8-bit or 10-bit, and this really is only the ease of getting the results. You can either get it in one register or putting together two registers. The single register, if we wanted to use 8-bit, it's easier just to do what is called a left adjustment. To do the 10-bit, we'll have to do a tad bit more work, but we probably won't be doing the left adjustment. But we can still do it, but we may find it easier to have it right adjusted. We need to turn on the ADC. And this will be done mainly at the end of the configurations, because we want to turn it on as late as possible, just before we're doing the conversion process, because the ADC does take up, or does consume, some power. Because the ADC is rather slow, we need to enable a prescaler, and this is determined by our clock. And finally, we need to start the first conversion, and in the interrupts we need to start the next conversion. I'm just going to show a couple asterisks here to show that this is the code block. Inside the interrupt routine, we're going to actually, since we're not going to start, we're going to do this last. We're going to start the next conversion at the end of what we're going to be doing in the interrupt routine. So what we need to do is establish a variable that we will be using as a string for putting the number to the LCD. We also want to convert the result of the conversion, the ADC conversion result. We want to select a location on the LCD to put the number, and then we want to display the number, or the string that will be the number. So let's take a look at this and see what we might need to do. We know we need to convert the ADC conversion result to a string. We know we need to convert this to a string, so we're going to need the standard library up here, because we're going to be using the itoa command. And since we're using interrupts, we might as well go ahead and include that too. Interrupt.h. So these are essentially all the tasks that we need to do to have the analog to digital converter convert the analog voltages to a digital number and display it on the LCD. Let's go ahead and convert these into actual code and we'll see what we get. I'm first going to go and tackle the low-hanging fruit. So enabling the global interrupts is just simply putting SEI. So that's done. Since we know how the LCD works really well, we can go ahead and tackle those. We can go ahead and establish a string for the variable that will contain the string of the number that will be converted from the result of the ADC. Call that ADC result, and we'll make it a 4-digit number since we may get into the 10-bit conversions, so that would be a total of 4 digits since 1024 is far away from a 5-digit number, so we'd be safe using 4 digits here. Even if we had it offset and we're going from negative to positive, we wanted negative 512 to positive 512, we'd still be safe even with the negative sign, since the 1024 would be cut in half and that would convert into a 3-digit number, 512 maximum, and then a negative sign would be another one for 4 digits. We know what the next line would be, and that would be the ITOA command. We don't know what the value is right now, but I'm just going to put in value of ADC result. We can put that in later if we want to. Then the string is going to be called the ADC result, and we're using base 10 so we can read this number as humans. Selecting a location to view this number. This is pretty easy. That's the go to Mr. LCD location. And I'm going to make this simple. I'm just going to put it on the first row and first column. X and Y will be 1. And then we're going to simply display the number on the LCD. So we're going to send a string, and it will be ADC result. We don't need this remark anymore. So let's go ahead and do all of these pieces here, configuring the ADC. And we're going to be doing enabling the interrupts. We're going to determine whether we want a left or right adjusted result, and we're going to enable the prescaler. The turning on the ADC feature should be the second to the last thing that's done in this section, and the last thing should be start the first conversion, because that's when it actually begins the conversion process, and it tries to read the potentiometer's voltage, or the voltage that is on the middle pin of the potentiometer. There is one thing that we want to address before we start to convert these lines into code, and that is, you may be wondering, we didn't set up which pin we're going to be using for the ADC. Let's take a look at the pinout for this chip, and you'll notice that there are 7 ADCs. There's ADC 0. We have ours plugged into ADC 0 all the way to ADC 7. So we don't have a line here in our programming that states select the right pin or select a particular pin. And you are accustomed to doing that because of the ports and looking at pins and ports. But the ADC works a little bit differently, and it uses a multiplexer. Let's take a second and look at the data sheet where it starts to discuss the multiplexer. And on page 214 and 215, you will notice there is a MUX 4 to 0. And these are 5 positions, indexing from 0. You'll have zeros all the way across if you're using ADC 0. You'll have this 1 position if it's ADC 1, and you'll look at the second position if it's ADC 2, and then it counts up in binary for the remaining ADCs. You'll also notice that you can change the gain and have positive differential input and negative differential input. I won't be getting into those in this particular tutorial, but it's good to know that this is selected with the MUX, the multiplexer. And also, since there are all zeros here, we don't actually need to specify ADC 0 because it's at default it will select ADC 0. Only when we need to set a 1 in one of the MUX positions will we, if we needed to use another ADC pin. So let's go back to the code and see which line we want to convert to code first. I would like to first look at how to turn on the ADC feature. So let's go back to the data sheet and see how we can do that. In the data sheet on page 216, we have the ADC control and status register A. And you'll see that there is an ADC enable. That is the bit that we need to turn on. It's bit number 7. You can also see it right here. And we need to put a 1 in bit number 7, or the ADEN. So let's go ahead and do that. We're going to remove this line. The control register was ADC SRA, all caps. And then we're going to do a logical OR equals, and we're going to put a 1, shift it with the shift operation, and ADEN. So now we have turned it on just with this single line here. Now we need to enable the prescaler. Now we have to calculate what our clock is. Right now I'm running at 1 megahertz, so I'm just going to put in 1,000,000, and we're going to divide that by a prescaler to get to the hertz that we, or the kilohertz actually, that we were allowed to use. Let's go to the data sheet to find out what that is. Okay, we have the prescalers here is ADP S2, S1, and S0. And let's see what it says about that. It doesn't really give me much information in this portion of the data sheet, but in the beginning it does, and we need to find out what our minimum and maximum tolerance is for the slowness of the ADC. So I'm going to go up to the top. So it's telling us right here that we need an input clock frequency between 50 kilohertz and 200 kilohertz. So what we need to do is get that prescaler, and we need to divide 1 million by that prescaler to find out if we can get between the 50 and the 200 kilohertz. Another way we can do that is divide the million by 50 kilohertz and find out what that number would be, and then divide it by the 200, and we'll have our range, and we can find out where that number, what prescaler we need to use, what prescaler fits between those two numbers. So let's go ahead and do that. So we can take our million divided by 50, and that's actually, we're dividing it by 50,000 because that's kilohertz. We could do, if we wanted to simplify this, we can just take out 4 zeros on both sides, and then we have 100 divided by 5, which is equal to 20. And now if we want to look at the other one, which is 1 million divided by 200,000, or 200 kilohertz, we can take out all of these zeros. 1, 2, 3, 4, 5. Take out these 1, 2, 3, 4, 5, and then we have 5. So we need to find a prescaler between 5 and 20. Let's see if we can find one. Now let me mention one thing. You can actually go outside of these frequencies, because it tells you that only if a lower resolution than 10 bits is needed, the clock frequency, input clock frequency to the ADC can be higher than 200 kilohertz. So you could, if you're only looking for 8 bits, then you can actually go higher than 200 kilohertz. So let's go ahead and find the prescalers. Okay, here we go. So it looks like we could probably use 16 because that's between 5 and 20. We could also use 8. We cannot use 32. I'm going to go ahead and just use 16. That should be fine. Let's go back to the program. Actually, we need to figure out, let's see, we have to have ADPS2 should be equal to 1. Oh, I'm sorry, yeah, should be equal to 1. The other ones are 0 as default. So we'll just look at this one and we'll set this particular one, ADPS2. So that was ADPS2, ADPS2, and we're going to be using, that's going to be in the control register, ADC SRA, and we're going to do a logical OR again. Alright, let me just go ahead and make sure that was in the control register here. Yes, we have those three, and this is the control register. Let's go back to the program, let's see what else we need to do. We can take this out, we don't need this anymore. Okay, we need to do a left shift or a right shift on the results. Set it so it will shove all of the numbers, all of the bits to the left or the right. So let's take a look at the data sheet and see what it says about that. Okay, if ADLAR, which is if it's 0 shifting to the left, or if it's 1 shifting to the left, you can see how the ADCH, it only has 2 bits that are set, and this is part of the 10-bit number. We could actually use this as when we're trying to get 10 bits of a value for the result. We can easily just put this one right before the ADCL. We can combine those 2 bits or we can combine those two binary numbers and we'll get a 1 10-bit number. And you can see that it's using from 0 to 9, which is 10 bits, indexing from 0. But if we use the ADLAR, it'll be much easier just to get the 8-bit number, which is from 2 to 9. And we're going to set the ADLAR to 1, so we can just look at the this ADCH to get the result that we want from 0 to 255. So let's take the ADLAR, which is in the control register, and we'll set that to 1. ADSCRA, ADC SRA. I want to do all, I want to do all these before turning on. All right, and this looks like it's the wrong character. So we'll do another logical OR equals 1 shifting to the left the ADLAR bit or bit number. So we've done this. Now we need to enable the interrupts for the ADC. One thing I didn't do is confirm to see if the ADLAR is actually in this register. So let's go ahead and do that. We have to make sure we pick the right register for these, and I know I didn't because I looked at my other program. So we can see that ADLAR is not in the control or status register. Let's see if it's in the MUX register. Yep, add MUX, and we have the ADLAR there. So let's change the registers here. ADMUX. Now that should work fine. Now let's look to see how we enable the interrupts for the ADC. Okay, let's go back to the data sheet and check. We don't have anything in here that would have anything to do with the interrupts, but it will be in the control register, which makes sense. Alright, we have the interrupt flag. This will be set when the ADC conversion completes. We don't really need to worry about that right now. This will be automatically set by hardware. We could use this to check to see if the ADC conversion completes, but it'll automatically go into our little routine anyway. So we can use the ADIE to enable the interrupt. So we want to put a 1 in this bit, which is bit number 3. Let's make sure that's in here. ADIE and ADSCRA. So we're going to enable this one by putting a 1 in bit number 3. ADIE. And that was the ADIE, which is the interrupt enable for the analog digital interrupt enable. So we've done that. We can eliminate this remark. Okay, so now we can go ahead and put in the code to start the first conversion. Let's check the data sheet and see how we do that. Okay, it looks like the start conversion is here. We can put a bit, or we can put a 1 in bit number 6, which is the ADSC. So let's go ahead and do that. ADC SRA. Can't remember what it said actually. ADSC, start conversion. AD, analog to digital. S for start, C for conversion. Okay. I want to actually put this global interrupt right after I enable the interrupt. I actually don't know if it'll matter or not, but I always like to be safe. You can try it outside, maybe in the after it, and see what happens after you start a conversion and then start the global interrupts. But I have a feeling that it may break down at that point. So I'm going to go ahead and put the global interrupts before the starting of the conversion. Let me get rid of that. Okay, so now we can set up our interrupt vector for our routine. And that will be the only thing we need to do, except for actually, we need to start the next conversion. So all we have to do here is repeat this statement. Once it's converted, finished converting, and we have used the values, we can go ahead and start another conversion. And then once the next conversion is complete, it'll come back into this routine. All right, we know that doing an interrupt service routine is ISR, and then we're going to put something in. We're going to put the vector within these parentheses, and we'll use our code block brackets. Alright, so let's see what this vector is. Okay, so the vector for the ISR is called the ADC vector, the analog to digital converter vector. Now I'm going to have a list of all the vectors for all of the interrupts on the website. So you can find whatever vector you need to use there, and I will also have code samples to show if I have those code samples available. I'll put the code sample in there for that particular vector. Okay, so this, let me take this and format it a little bit. Okay, so there's one more thing that we need to do, and we need to actually find the value of the result. And let's go back to the data sheet. Okay, so we're looking for the actual value. The values are in ADCL and ADCH. This is analog to digital conversion low and analog to digital conversion high. And we're going to use the one that, because we left adjusted it, we're going to use this particular one, which is the ADCH, which it's the high set of binary numbers, the high set of the bits, the high set of the high portion of the binary numbers. So let's go ahead and take the ADCH and put that into the value. We're just going to put ADCH right here, because that's going to be automatically available when we have this vector, when this vector fires and the program stops execution with the never-ending loop. It will automatically go into this vector routine, and the ADCH will be available automatically. Once we start a new conversion, the ADCH will be disposed and we'll get a new one once it gets back into this interrupt service routine. I just noticed that I don't have a semicolon after my declaration here, so I put that one in. And I noticed also I forgot the S because it's go to Mr. LCD's location. There is a very important function that we haven't addressed yet, and that is, how are we getting the reference voltage? What is going to be our top threshold of voltage, or our top measurement of voltage? We have to have some way for the microcontroller to know what is our highest voltage limit for the ADC to use. And the way we have it set up in the circuit, we're using the AVCC, the analog digital controller main power pin. And we're going to be reading that power pin as our voltage reference. So we have to figure out how to do that. So let's go to the data sheet and find where that's located. And if I remember correctly, it's in the ADMUX register. Okay, here this is the table that we're really interested in, and it is in the ADMUX because we have the ref S1 and S2 here. This is FS1, ref S1 and ref S2, and this is using the AREF when the we'll be using this later on in other tutorials where we have a different voltage for the device that we're trying to sense the voltage. But right now we're going to be using the AVCC pin. And we also didn't put a capacitor on the AREF pin, but we're going to try it without it first. And if it works fine, then we'll try it with it and see if it has a cleaner signal. But this is only to make sure that the AREF is not going to be interfering. The capacitor on the AREF pin is only so that there will be no noise coming in from the AREF pin when we're using the AVCC. So let's go ahead and set ref S0 to 1. And this was in the ADMUX. And that was the REFS0. Okay. So let's go ahead and make and program and see what we have. The microcontroller has been programmed, and we can see that there is a 255 on the LCD screen. If I turn the potentiometer, the number will be going down. But notice that there is a leading 0 here, which is undesirable. I didn't erase the zeros that are after the number while it was counting down. So let's go ahead and put in a little bit of code to make sure that those zeros are not going to exist while it's counting down. Okay, so we noticed that there were zeros following the numbers when those zeros should have been erased. So all I'm going to do is add just a space after the send a string. We're going to send another string, and we're just going to put a space in here, and this space will happen right after the number. So as the number goes down, there will be a space, and anything that was there will be erased. So we're going to go ahead and make and program this one and see the results. Okay, we've reprogrammed with that space added. You'll notice that there's a space and then there's a cursor at the end. If that is annoying to you, you can just turn the cursor off using the special send a command that we talked about in the LCD videos. And let's see what happens when we turn the potentiometer. And it looks like it's working correctly. I stopped it, started it again, stopped it. There you go, all the way to 0. So we have only a 0 there, which is exactly what we want. So that is how you read a potentiometer using the analog to digital converter. We'll be now doing quite a number of tests with different sensors and see how we can read sensors and also use other voltage references, because we'll have these sensors using different their own voltage ratings. So we'll have to tap into their power supply, and we'll essentially have to make a power supply for them, or we'll need to run the microcontroller at a lower voltage. I'm using the ATmega32. I'll need to switch this one to the 324 so I can go to a lower voltage, and we may be doing that on the next video. Thanks for watching.